This is Kelly Hill, technology reporter for RCR Wireless News. I'm here today with Christoph Pointner of Rohde Schwarz, and you just finished up a couple of presentations this morning at the 5G Innovation Summit. Tell us a little bit of your key takeaways, and then also, what is Rohde Schwarz doing in terms of supporting 5G test?
Yeah, okay, thank you very much, Kelly. Key takeaway, and I think I've tried to explain it throughout the morning and the afternoon, is we are losing antenna connectors on our devices. So the nice world of a nicely calibrated test system, path losses through cables, that's all going away, because what we have to do is over-the-air testing, which on one side is a very good approach because it's a known approach already. We have test plans in place and we know what we are doing. On the other hand, it still gets more complicated because of calibration issues, because of all of a sudden we add a new dimension to our testing, and we have power measurements, for example, that are dependent on space. It's the orientation of the device on the test towards the test antenna that all of a sudden matters.
And you guys did some interesting testing, I think, that you mentioned that showed the difference between the results in terms of, you changed the orientation of the device and the radiation patterns are very different.
So first of all, we had to build a repeatable and reliable test environment, which for over-the-air always means, even at higher frequencies, we need to use anechoic environments. But what we needed to do was to create this perfect link between our test antenna and the antenna of the device under test. So to replicate as closely as possible the cable we have today by an over-the-air link. So what we did, we used a TDD device at 2.6 gigahertz, and we had it wired up first. So we did our conducted measurements the way we know them for EVM, for spectrum mask and other signal quality measurements. And then we repeated the same measurements over the air. But to do that, we needed to find out what is the best orientation to do so. And we just limited to 6 basic orientations, like the face of the die. And we could already see that for 3 of these setups, there was no correlation whatsoever to our conducted measurement. But for others, we could see that we have a good link. And we could see that for transmit measurements, EVM, spectrum mask, we had a good correlation with the conducted measurements. For receive measurements in a SISO case as well. But when we implemented the multiple receivers and we tried to measure that on the conducted device, we had the expected 3 dB improvements. And on the radiated measurements, we could see the crosstalk that's happening between the different antennas, and we didn't see the same results.
Okay, great. So let's just talk about that a little bit more. What do you think will be some of the fundamental challenges that we'll have to deal with? Obviously OTA testing is one that's expected to be greater as we moved into 5G. Are there other testing challenges that you see? You mentioned near field, far field. That change is very. I think that's a little different when we start getting into much shorter wavelengths.
Yeah, so I was recently at an event where an antenna manufacturer mentioned 5G is all frequencies. So it's basically from 0 to 100 gigahertz, something like this. And this is where these challenges, as you said, near field and far field measurements really come into the equation. Because, everyone says, yeah, with higher frequencies it's going to be easier and we can go much closer to the device in the test for a measurement. But we mustn't forget that the size of the aperture is really important. And then since 5G is not only 28 gigahertz, 39 or beyond 60 gigahertz, but also sub-6, where we have a smaller wavelength, test distances play a matter, and then we need to implement and use algorithms like near field to far field transformation for pattern measurements, and that makes the setup a bit more complicated, especially with active devices where we have to do phase retrieval measures. But the good thing about this is, and there's an answer to it, and there is systems that can do it, and there is setups where we can do this. It's just getting a bit more time consuming, the measurement as such.
Okay. All right. Well, thank you so much for your time, Christoph.
Thank you very much for giving me the opportunity, Kelly.